Welcome to this lecture. The equations of induction machine in phase variable, that is in ABC variables of the stator and ABC variables of the rotor. We have also derived the expression for the torque in ABC variable, which was little complicated. Now, if you see the equation for the torque in ABC variable, let us see this slide. We have the energy stored in the field WF is half IABCS transpose LSS minus LLSI into IABCS plus IABCS LSR prime into IABCR prime plus half IABCR prime transpose of LRR prime minus LLR prime into I matrix multiplied by IABCR prime. So, this equation is the equation for energy stored in the coupling field. Now, we have assumed at the very beginning that the system is linear. It means the magnetic circuit is a linear magnetic circuit, there is no saturation. Hence, we can assume that the energy is equal to the co-energy. So, we can say that WF is the energy stored in the magnetic field is same as WC is the co-energy of the magnetic field. And we also know that if we want to find out the torque is the derivative of the co-energy with respect to theta r, that is given by this particular expression. The TE is the torque generated by the machine is equal to P by 2 is multiplied, because we have assumed theta r is the electrical speed. WC is the expression that we have already seen, and it is dWc by dr at constant current. So, we can assume that all the currents of the stator and the rotor are kept constant when we are doing the differentiation. This is a partial derivative with respect to theta r. Now, if we differentiate this equation has got three distinct terms. One is the self inductance part, that is LSS minus LLS into I. Now, we are subtracting the leakage because leakage flux does not help in the energy transfer. In other words, the leakage flux is not present in the coupling field. The coupling field is a field due to the mutual flux, the flux that links both the stator and the rotor. So, one component of the flux is due to the primary, that is half of LLS into LLSI IABCS, and the other component is the flux which is the mutual flux, and the third component is the rotor self inductance flux. So, out of these three components, we can say this is the first component, the stator self inductance flux, and then this is the rotor self inductance flux, and the third component here is the mutual flux, or the energy stored due to the mutual flux. And when we differentiate this with respect to theta r, we will see that the first term, the term 1 and the term 2, term 3, these two terms are independent of theta r. They are not function of theta r. Only the mutual term, that is term 2, is a function of theta r. Okay. Now, this term is a function of theta r. So, the differentiation of the first term and the third term will be equal to 0. So, we will just differentiate the second term. So, this is the differentiation of the second term with respect to theta r, and then we differentiate and simplify, because the currents are constant, IABCS and IABCR, these two currents are constant. So, we have to only differentiate the matrix, that is LSR prime, and LSR prime is the mutual inductance matrix between the rotor and the stator, and this matrix is obviously a function of theta r, as we have seen in the previous lecture. Now, when we differentiate this matrix with respect to theta r and simplify, we get the following expression for the torque. It is minus of P by 2 into LMS into this expression. Now, we see that this expression is a complex expression which involves both the stator and the rotor currents, the stator currents are IAS, IBS, ICS, and the rotor currents are IAR, IBR, ICR, and also this involves sin theta r and cos theta r. As you can see here, we have sin theta r component here, we have cos theta r component here, we have IAR prime, IBR prime, ICS, the stator component of current, the phase C, IBS is the phase B of the stator current, IAS is the phase A of the stator current, and similarly we can see this also contains the rotor current, the stator currents, and this little complex. So, we have already seen that the torque expression can be derived, but it is complex. So, when we simulate the machine in ABC frame, we can do it and we can do it exactly. We can do it as if we are energizing a real 3-phase machine. We can apply the 3 voltages VA, VB, VC, and we can observe the 6 currents, that is the 3 for the stator and 3 for the rotor, IAS, IBS, ICS for the stator and IAR, IBR, ICR for the rotor. And then we can derive the torque equation, and from the torque equation we can find out the equation for the speed. TE is equal to J d omega r by dt by P by 2, because omega r is the electrical speed, plus B by P by 2 into omega r. B is the coefficient of viscous friction, omega r is the electrical speed, plus the load torque. So, when we solve this equation, we can find out the expression for the rotor speed, that is omega r. Omega r is the electrical speed of the rotor, and theta r can be obtained by the integration of omega r, and this theta r can be substituted back to evaluate the inductance matrix and also the expression for the torque. So, this basically goes in iterative process, and we have to solve these equations by numerical methods using computers, and after the first iteration we can evaluate the torque, the speed and the rotor angle, that is theta r, and theta r can be substituted back to recalculate the inductance matrix and the expression for the torque. So, this goes in iterative process till we reach the final time, the time to stop the simulation. So, this is possible, but this involves lot of complexities, and this is going to consume lot of computer CPU time. Now, to simplify the simulation, we can go for DQ modeling, which means we can transform the ABC variables into DQ variables, and then without simulating in actual ABC variable, we can simulate the machine in DQ variables to get the expression for the torque and the speed. So, we will go for the transformation right now. Now, to be able to do that, we have to transform the ABC variable into DQ variables. So, we will discuss the transformation in induction machine. So, we will take a normal 3-phase machine with phase A, phase B and phase C in the stator. This is phase A, this is phase B, this is phase C of the stator. And in a similar way, we can take the rotor, this is the rotor, this is phase C of the rotor, and this angle is the rotor angle, that is theta r. A rotor is rotating at a speed of omega r in the anti-clockwise direction. So, this is basically our 3-phase machine that we are talking about. This is our AR, BR and CR. Now, what we would like to do, we would like to transform this machine into a DQ machine. So, this is a rotor and we have two rotor windings. There is the pseudo stationary winding, one in the D axis and the other one in the Q axis. So, this is our D axis. And this axis is the Q axis. So, we have a D axis stator, we have a D axis rotor, we have a Q axis stator and we have a Q axis rotor. So, we can call this to be DS, this to be DR, and these two windings are coupled. So, we can have dot here, and this is QS and this winding is QR. This winding is coupled with this winding. So, we can show some polarity marking here. So, this is what we have here. Okay. All right. Now, in this case the objective is that we have to transform the original machine into DQ machine. So, what we do here, the original machine has got the number of turns per phase is NS here, and this number of turns we can call this to be also NS. So, we can assume that the number of turns of the actual machine is same as the number of turns of the DQ machine. DQ machine is a hypothetical machine. It does not really exist in practice, but for our own convenience we are transforming the ABC machine into a DQ machine, and we have equalized the number of turns NS in the stator in the 3-phase machine and the same number of turns per phase for the 2-phase machine or 2-axis machine. So, here also we have NS in this case. The rotor is NR number of turns. Here also we have NR here and NR here. Now, we can now write down the MMF balance equation. Whatever is realized by a 3-phase machine has to be realized by a 2-phase machine. So, first of all what we do here, we equalize the ampere turns, equalize the MMFs. So, what we do here, we can write down the equation of the MMF in the D axis. So, we can say that NS IDS is the D axis MMF produced by the DQ winding in the stator, and that is equal to NS into IA plus IB cos 120 plus IC cos of 240 degree. Now, if you see, the MMF produced by the D axis stator will be same as the MMF produced by the ABC stator in the D axis. So, we can resolve this MMF produced by B phase and C phase onto this D axis here. This is also the D axis, and this axis is the Q axis. We have defined these two axes and we are talking about stationary DQ axis. This DQ axis are stationary in the space, they are not moving, they are stationary with the stator. So, if we resolve this MMF, this will be, this current is IAS in the stator, this current is IBS, this current is ICS. So, what we do here, we project the phase B MMF and phase C MMF and phase A MMF all along the D axis, which is aligned along phase A of the stator, and we equalize the MMF of the DQ machine and the ABC machine in the stator. So, that is what we have written here, cos 120 for phase B and cos 240 for phase C. Now, if we simplify this, what we have here is the following, that is equal to NS into IA cos 120 is minus root 3 by 2 IB, and this is plus root 3 by 2 IC. So, this is NS into IDS. So, if we simplify this, we can say that, yeah, there is one simple thing. So, this is actually minus half and minus half. This is half and minus half. So, we can simplify this. IDS equal to IA minus of half IB minus of half IC. So, the stator currents are IAS, IBS, ICS. So, we can make this currents as IAS, IBS and ICS. So, this is IDS. In a similar fashion, we can equalize the MMFs in the Q axis. So, what we can say here is that NS into IQS, that is equal to NS. Now, if you simplify this, this will be IBS root 3 by 2 minus ICS root 3 by 2. So, what we are trying to do here, we are equalizing the MMFs in the Q axis. So, what we can do here is that we can project all these MMFs in the Q axis and equalizing with that of the DQ machine. So, we get the following expression, that NS into IQS is equal to NS into IBS into root 3 by 2 minus ICS into root 3 by 2. NS and NS will be cancelled. We can say that IQS equal to IBS root 3 by 2 minus ICS root 3 by 2. So, this is actually the stator transformation. It means we are able to transform the currents ABC into DQ current of the DQ machine. And in addition to the DQ component, we can sometimes also have the zero sequence component IOS, and that is equal to 1/3 of IAS plus IBS plus ICS. So, IOS is a zero sequence component, and here that is equal to 1/3 of IAS plus IBS plus ICS. So, we have IDS, we have IQS, we have IOS. Now, when we transform, sometimes we can have this transformation and transform the ABC into DQ axis machine, and we can get IDS, IQS and IOS. Now, what we do in addition to that, we always aim that this transformation will not alter the parameters of the original machine. Actually, the parameters are all given in the per phase of the actual 3-phase machine, and when we transform this into ABC machine, the per phase parameters should not change. So, the objective here is that while transforming, we are keeping the per phase exactly same. It means the per phase of the ABC machine should be same as the per phase of the DQ machine. So, we can write this in a matrix expression, that we have got IDS, IQS and IOS, and these are basically obtained from the original machine currents, and these currents are IAS, IBS and ICS. And what is this matrix? We have seen this is 1 minus half, 0 root 3 by 2 minus root 3 by 2, and here it was 1/3, 1/3 and 1/3. So, we will just multiply here a factor of 2 by 3, and here we will have half, half and half. So, this is the transformation matrix, that is CS. Now, the question is that how did we obtain this 2 by 3? Now, this 2 by 3 comes into picture to equalize the per phase variables. It means the per phase currents and the per phase voltage should be the same, and we have to use the same transformation for the current, voltage and flux linkage. So, if this is my CS, I can also write down IDQOS, that is equal to CS IABCS. So, the transformation is valid for the current. It means it can transform IABCS into IDQS. The same transformation can be used for the voltage, and the same transformation can be used for the flux linkage. So, if this is my CS, I can write down IDQOS, that is equal to CS IABCS. So, the transformation is valid for the current. It means it can transform IABCS into IDQS. The same transformation can be used for the voltage, So, I can use the same transformation for the voltage. I can also use the same transformation for the flux linkage. So, these are all vectors, the flux linkage, the voltage and the currents are all vectors. So, we are using the transformation matrix, that is CS, to transform the current, voltage and flux linkage into that of the DQ machine. And since we are talking about per phase power invariance and per phase variable should not change, it means per phase impedance should be the same, per phase current should be the same, per phase voltage should be the same, and per phase flux linkage of the 3-phase machine is same as the per phase flux linkage of the DQ machine. We choose this factor as 2/3. It is basically a constant that we are choosing, and this constant in general could have been a constant k, and when we take per phase power invariance, keeping the parameters exactly the same, this constant k turns out to be 2/3. Okay. So, this is for the stator. And what about for the rotor? Similarly, we can also have for the rotor. So, for the rotor we can have a similar transformation, but that transformation will involve the rotor angle. Now, we can now do the rotor transformation, and similarly the rotor, if you see that we are transforming this AR, BR, CR to DR and QR. Again, the rotor is also transformed into a 2-axis model. So, we have to project the MMFs in the D and Q axis respectively and find out the DQ current for the rotors as well, as we have done for the stator. So, let us see how it comes out to. So, we can write down here NR IDR, that is equal to constant k into NR IAR cos theta r. We are equalizing the MMF in the D axis. That is why we have got in the left hand side NR IDR. In the right hand side, we can project the MMFs of ABC onto the D axis, plus IBR cos of theta r plus 2 pi by 3 plus ICR cos of theta r minus 2 pi by 3. Similarly, in the Q axis, some constant k in R IAR sin theta r. Here the cos will be replaced by sin, IBR sin of theta r plus 2 pi by 3 plus ICR sin of theta r minus of 2 pi by 3. And further we have the zero sequence component. We can straightforward write IOR equal to 1/3 of IAR plus IBR plus ICR. Again we choose k equal to 2 by 3 for phase power invariance, and we write down the matrix expression IDR, IQR, IOR to be equal to 2/3 of cos theta r plus 2 pi by 3 cos theta r minus 2 pi by 3 sin theta r plus 2 pi by 3 sin theta r minus 2 pi by 3 half half half. This is IAR, IBR, ICR. This is the rotor transformation. So, we have the rotor currents, and this matrix here is called the rotor transformation matrix, that is CR. So, what we have done here, we have been able to find out the transformation matrix for the stator and the transformation matrix for the rotor, and having found that, we can transform the equation in ABC variable into the equations in the DQ variable. So, this transformation IABC R can be transformed into IDQ R. So, we can say and this is valid for the voltage as well. Also for the flux linkage. So, we can say here psi dqr also equal to CR psi ABCR. So, the same transformation can be used for the current, voltage and flux linkage. That is the uniqueness of this transformation matrix, that is CR, when we choose k equal to 2 by 3. Now, with this help, let us transform the ABC equation into DQ equation. So, we start with the stator. First of all, we start with the stator equations. We can write down here VABCS, that is equal to RS IABCS, RS is a matrix, plus P psi ABCS, and we can pre-multiply this equation with CS. So, we can say that CS VABCS equal to CS RS, we can have CS inverse into CS IABCS plus CS P psi ABCS. So, we can write down this matrix in the stator equations. Okay, and the left hand side will be V DQOS, that is equal to CS RS CS inverse, right hand side in this case would be I DQOS, because this is CS into IABCS, that is I DQS, and CS being constant, it can be taken inside the derivative term. So, we can say here that is P CS psi ABCS. Now, let us try to expand this. Okay. Now, what is psi ABCS? Psi ABCS is the stator flux linkages in the phase A, phase B and phase C. So, this consists of two terms, the flux linkage due to the self inductance and the flux linkage due to the mutual inductance between the stator and the rotor. So, we can write down this as follows, that is LSS is the matrix into IABCS plus LSR into IABCR. Now, here when we write, we refer everything to the primary side, and hence we have this prime factor coming to picture, because all the variables are referred from the primary side. So, when they are referred from the primary side, they are multiplied by suitable number of terms, and hence we have the prime variable here. So, this has to be transformed. So, we can pre-multiply this equation by CS Cs psi ABCS, that is equal to Cs LSS Cs inverse into Cs IABCS plus Cs LSR prime, and we can have CR inverse into CR I ABC R. So, this equation that we have written just now will transform the inductances of the ABC machine into the inductances of the DQ machine. Now, we will see very interestingly, actual ABC machine inductances, some inductances are function of theta r. Now, when you transform this inductance into DQ machine, all inductances will be constant. They are independent of the rotor position, that is the theta r. Theta r is the rotor position, that all independent of the rotor position theta r. So, we will evaluate this inductance first. Now, Cs LSS Cs inverse. Let us evaluate this inductance. Now, this inductance is the stator self inductance. The stator self inductance, this is independent of theta r. Now, when we transform this into DQ model, this will be again independent of theta r, but with some new factors coming to picture as follows. Now, if you see this, that is equal to 2 by 3, I can write down what is Cs. Cs is 1 minus half 0 root 3 by 2 minus root 3 by 2 half and half. Now, what is LSS? If you recall, the LSS had the diagonal terms which were constants, and they also have the mutual terms. Okay, the diagonal terms are LLS plus LMS, LLS plus LMS, LLS plus LMS. Now, the mutual terms are minus of half LMS, minus of half LMS, minus of half LMS, minus of half LMS, minus half LMS, minus half LMS. So, these are the mutual inductance between the two phases of the stator, stator A and stator B, and then we will post multiply this inductance matrix by Cs inverse. This is the Cs inverse. So, if you calculate what is Cs inverse, this is 1 minus half 0 root 3 by 2 minus root 3 by 2, and then what we have here is 1 1 and 1. So, if you multiply Cs and Cs inverse, we get the I matrix, all right. So, this is what we have here, and then we can simplify this one, and when we simplify this, we get the inductance matrix of the DQ machine, and that is LLS plus 3 by 2 LMS 0 and 0, 0 LLS plus 3 by 2 LMS 0 0 0 and LLS. This is an interesting matrix in the sense that most of the elements are zeros here, only the diagonal elements are present, all the off diagonal elements are 0, and that is happening because there is no coupling between the D and Q axis. Now, if you see a DQ machine, in this case we have transformed the original ABC machine into DQ machine, and when we find out the inductance of the D matrix or the D axis inductance, the D axis inductance is independent of the Q axis inductance. The D and Q axis are orthogonal to each other, and they are perfectly decoupled, and hence the off diagonal elements are becoming 0. And then in addition to the DQ inductance, we also have the zero sequence inductance. And what is the zero sequence winding? The zero sequence winding does not have any coupling with D and Q axis. It can be assumed that it is a winding in the Z direction or in a plane perpendicular to the plane of the slide. Okay? So, we can we can think like that, that this is the zero sequence inductance. This is the inductance of the q axis stator. So, we can call this to be Qs, this is Os, and what about this? This is the inductance of the d axis stator, that is LDS. Okay. Okay. So, we have already seen that this is the inductance matrix of the stator in the dq model, which does not have any off diagonal terms, and we also see that LDS equal to LQS. LDS equal to LQS, we can say that is equal to LS, the stator inductance of the d and q axis. So, that is equal to LLS plus 3 by 2 times LMS. Now, if we see this 3 by 2 terms is coming because of the fact that this is the equivalent of a 3-phase machine. So, LMS is the individual magnetizing inductance of the ABC machine. When you transform this ABC machine into a DQ machine, because of the coupling of the ABC phase, this coupling is reflected as 3 by 2 times of LMS in the DQ machine. And normally when you have an induction machine, we do various tests to find out the parameters. We do the no load test to find out the parameters like magnetizing inductance, and we do the load test or the block rotor test to find out the inductances, the leakage inductances of the stator and rotor, also the resistance of the rotor. So, this inductance, which is the magnetizing inductance calculated in the no load test, is not LMS, it is 3 by 2 times LMS. This 3 by 2 times is coming, although it is a per phase magnetizing inductance, the 3 by 2 times term is coming because of the coupling between A, B and C. So, this shows the effect of coupling of A, B and C phases of the stator. So, similarly we can evaluate the mutual inductance. We can transform this LCS, LSR prime into CR prime. Now, if we simplify this, CS is 2 by 3, this is 0, root 3 by 2 minus root 3 by 2, half, half and half. Now, what is LSR? LSR is the mutual inductance between the stator and the rotor. Now, this inductance is a function of theta r. So, if we see this inductance we have derived in the last lecture, and this inductance was a function of theta r in the following fashion. So, this is cos theta r plus 2 pi by 3 cos theta r minus 2 pi by 3 cos theta r minus 2 pi by 3 cos theta r plus 2 pi by 3 cos theta r plus 2 pi by 3 cos theta r minus 2 pi by 3 and cos theta r, and this is post multiplied by CR inverse. Now, what is CR inverse? CR inverse is the following. This is cos theta r plus 2 pi by 3 cos theta r minus 2 pi by 3 sin theta r plus 2 pi by 3 sin theta r minus 2 pi by 3 and 1, 1 and 1. So, this is the last column of this particular matrix. Now, if you simplify this, this will turn out to be the following matrix. It is 3 by 2 times LMS 0 and 0, 0, 3 by 2 LMS 0, 0, 0 and 0. So, this is the matrix which is independent of theta r, although we have seen that originally the mutual inductance matrix between the stator and the rotor is a function of theta r. After transformation into dq system, we see that the inductance matrix that we obtain is independent of theta r. Hence, it is worthwhile to simulate the machine in dq model, because the inductances are independent of theta r, as we have seen in the following expression. So, this is the magnetizing inductance of the d axis, this is the magnetizing inductance of the q axis, and this is corresponding to the zero sequence component. And since the zero sequence component does not produce any coupling, it does not have any magnetizing inductance, and that is corresponding to 0. So, this is obviously coming because of the transformation, and in the dq model we have seen that the inductances are not function of the rotor position, that is independent of theta r. So, with this background we can write down the equation of the induction machine in a stationary reference frame or in the stator reference frame. So, we can write down equations of induction machine in stator dq axis reference frame. So, we can write down the equation for the stator and equation for the rotor in the following fashion: VDS is equal to RS IDS plus P psi ds, VQS is equal to RS IQS plus P psi QS, VOS equal to RS IOS plus P psi OS, VDR prime equal to RR prime IDR prime plus P psi IDR prime. All the variables are referred from the primary side, plus omega r psi QR prime, VQR prime equal to RR prime IQR prime plus P psi QR prime minus omega r psi dr prime, V OR prime is equal to RR prime IOR prime plus P psi OR prime. Now, these are the equations of an induction machine in stationary dq reference frame. Now, if you see this flux linkages psi ds, psi qs can be expressed in terms of the inductances, because we have been able to find out the inductances, and then these flux linkages also can be written in terms of the inductances. And we have seen that the rotor is rotating, and hence there will be rotationally induced EMF in the rotor. These are the rotationally induced EMF. All right, and the rotor is rotating in which direction? If we see the direction of the rotation is from A to B to C, phase A, phase B of the stator, phase C of the stator. We are assuming that the revolving field is rotating from A to B to C. So, the revolving field is in anticlockwise direction, and the rotor is trying to catch up with the rotating field, and that is rotating in the anticlockwise direction. This anticlockwise direction is in opposition to the convention that we have already set for the Cron primitive machine model. In the Cron primitive machine model, the rotor was rotating at a speed of omega r in the clockwise direction. All right. So, hence, if you see here, due to that we have plus in the d axis, that is omega r into psi q r, and then we have minus in the q axis equation omega r into psi dr, which was in opposition to the direction of the rotational induced EMF of the Cron primitive machine. but does not matter. If the direction is reversed, the direction of the rotational EMF will also be reversed. Okay? Nothing else will be changing, only the direction of the rotationally induced EMF will change. So, we can write down the flux linkages in terms of the inductances. Now, what are the flux linkages? We have got psi ds. Now, what is psi ds? Psi ds is equal to Ls IDS plus Lm into IDS. Now, what is Lm? Lm is 3/2 times of Lms. And what is Ls? Ls, as we have already obtained, that is equal to the leakage inductance of the stator plus 3/2 times the magnetizing inductance of the per phase of the ABC machine. So, this is the Ls, the stator inductance of the DQ machine. Similarly, we can write down the flux linkage in the q axis. Psi qs is equal to Ls IQs plus Lm IQr. Psi dr is equal to Lr IDR plus Lm into IDS, and psi qr is equal to Lr IQr plus Lm into IQs. Now, here the air gap is uniform. In case of an induction machine, there is no saliency. The stator is cylindrical, the rotor is also a cylindrical structure. The air gap is absolutely constant throughout the periphery of the rotor, and hence the inductance for any given position of the rotor is constant. The rotor is rotating, no doubt, but the inductance of the D and Q axis are constant, and LDS equal to LQS due to the fact that there is no saliency in an induction machine. So, we can say that we have the same inductance in the D axis rotor, the same inductance in the Q axis rotor, the same inductance in the D axis stator, the same inductance in the Q axis stator. Now, what about Lr prime? Lr prime is equal to Lr prime plus 3/2 times of Lms. So, we have all these inductance matrices, and from the flux linkages, the flux linkages can be expressed in terms of inductance and current, as you have shown here. These are basically the flux linkages, and they are expressed in terms of the current, and we can substitute this back into the original, and we have the zero sequence winding in this case, the zero sequence in the stator and the zero sequence in the rotor. These two components can be neglected so far as the torque production is concerned. The zero sequence components do not take part in production of the torque, and hence the zero sequence equations can be conveniently avoided while calculating the machine torque and machine speed. So, we can say that this can be avoided, can be ignored for torque calculation. And furthermore, the zero sequence components do not have any coupling with either D axis or Q axis. Since the zero sequence component do not have any coupling, I mean, if you ignore that particular equation, you do not need IOR anywhere. We do not need IOS anywhere. So, since IOS and IOR are not required in the equations for the calculation of torque or otherwise, we can avoid the computation of zero sequence currents in the stator as well as in the rotor. Now, why then we show them in the equation form? Now, we show them in the equation form because to reconstruct back the ABC equations, if you want to transform ID, IQ into ABC, you have to take help of the zero sequence component. The zero sequence component, although does not take part in torque production, will be helpful in calculating back the ABC variables. Okay. So, we can now write down the expression for the voltages, and we can write them in a matrix form: VDS, VQS, VDR and VQR. We just have 4 variables as opposed to 6 variable in ABC frame. So, we can just write down the currents and fill up this impedance matrix IDS, IQS, IDR and IQS. So, we have a 4 by 4 matrix and we can write down this just by inspection. We do not have to remember. The first one is the stator resistance drop and the stator self inductance drop. So, we can say it is RS plus LSP. Now, the stator d axis rotor is coupled with the d axis stator. So, we have LMP and then the stator does not have any rotational induced EMF. So, we can make the other terms equal to 0. The first row has been evaluated. Similarly, the second row we have RS plus LSP in the q axis stator, the resistance is the same, the inductance of the d and q axis are the same. Then we have coupling with the q axis rotor. There is no rotational induced EMF. So, we can make this element equal to 0. In the rotor, we have the rotor resistance drop, the rotor inductance drop, and then we have coupling with the d axis stator. Then we have to write down the elements corresponding to the rotationally induced EMF. So, this is in the d axis. So, we have omega r here into Lm, omega r here into Lr prime. There is a, this is the q axis one is coming into picture here. So, as per our previous equation, this is positive. So, we have this positive sign here. So, then here also we have plus sign in this case, and for the fourth row we have RR plus LR prime P. Now, this is the magnetizing inductance LMP. Then we have the rotational induced EMF here and rotationally induced EMF here, and the rotationally induced EMF is negative in this case. So, this is the equation of an induction machine in DQ model in the stationary frame. The stationary frame, the D and Q axis are not moving, they are stationary with respect to the machine stator. So, from this we can also evaluate the torque equation. How do we find out the torque equation for the primitive machine? We found out the torque equation by having this P by 2 I transpose Z I. So, this is my Z matrix or Z primitive. From this we can evaluate what is G matrix. G matrix is that part of the matrix which is associated with omega r term. So, we can evaluate what is the G matrix. So, G matrix we can evaluate, and we can rewrite this matrix G four by 4 matrix. There is no speed term in the first row, no speed term in the second row. There is some speed term here, and this is Lm and this is Lr, and this is minus of Lm and this is minus of Lr, and these are all zeros. Okay. So, we can see here we have minus Lm and minus Lr here, and here we have the speed terms plus Lm and plus Lr. So, these are present in this case, plus Lm plus Lr, minus Lm and minus Lr. Now, we can find out the expression for the torque. Te equal to P by 2 I transpose G into I So, if you simplify this, we can calculate the expression for the torque. This is the dq equation. We have dq here. So, I dq is equal to IDS, IQS, IDR, IQR transpose. So, these are the various currents. Now, if you pre-multiply this and post-multiply this, we can find out the expression for the torque. Now, when you find out the expression for the torque, we can evaluate the speed also. The speed can be evaluated from the electromechanical equation. T is equal to J by P by 2 into d omega r by dt plus B by P by 2 into omega r plus TL. So, we can simulate an induction machine in the dq reference frame. In the stationary reference frame, the dq axis are stationary, they are not rotating, they are stationary, and we have the voltage equations here. These are the voltage equations, and from this we can find out IDS, IQS, IDR and IQR, and then we can substitute this to find out the torque of the induction machine, and the torque can be substituted here to find out the speed. And since the inductance matrix in this case is not a function of theta r, this calculation is much faster than calculation in the ABC model. So, if you simulate an induction machine in ABC model, and if you simulate an induction machine in DQ model, an induction machine simulated in DQ model will be much faster than an induction machine simulated in ABC model. And after having simulated this ABC equations, and in the DQ model, we appreciate that DQ model is definitely better, and whenever we have DQ currents, we can transform them back into the ABC current. It means ID and IQ can be transformed back into IA, IB, IC. So, we are not losing anything in terms of the actual machine performance, but on the other hand, we are able to gain some computing time, because in DQ model the machine is simulated much faster than an ABC model. And from the ABC, from the DQ equation, we can get back the ABC equations as well. So, in this lecture we have seen how to simulate an induction machine in DQ model. We have also derived the expression for the torque, this expression, and in the next lecture we will see how an induction machine can be simulated in other reference frame, which is not stationary, which will be rotating in the space at any arbitrary speed omega. Omega minus omega r into psi qs, VQS equal to, this is omega s into psi qs,